Okay, in the previous lecture, I talked about electrophilic aromatic substitution. Electrophilic aromatic substitution. So we put electrophiles onto the ring, and to do so, we had to assume that the ring is a nucleophile. The ring in question is benzene. So for example, the first reaction we did was halogenation. Okay, so halogenation, which means we added halogen. So if you take a benzene ring and react it with bromine liquid and using the catalyst FeBr3, because we said bromine is not very polarized, you will replace any of the hydrogens sitting on the ring with a Br. So that replacement is what we call substitution. Okay, so if you use the Cl2 version with benzene, okay, then you'll have to use the Lewis catalyst FeCl3 version. And what that does, it's gonna replace the same hydrogen, one of the hydrogens on the ring is gonna be replaced with a Cl. So the electrophile, remember we say this is electrophilic aromatic substitution. This is an aromatic ring. This will give you the electrophile. You're substituting a hydrogen on the ring. The electrophile in example 1 will be Br plus, because that's what ends up on the ring. Electrophile in example 2 will be Cl plus. Okay, so these are the electrophiles, E pluses. They are attacked by the ring, which plays the role of a nucleophile. Always nucleophiles will attack electrophiles. Okay, now apart from that, we talked about alkylation. Okay, so for alkylation, there were two reactions, either by Friedel-Crafts alkylation. You can look at it in your notes. So where the one of the hydrogens is gonna be substituted with or substituted by an alkyl group. So an R group. So let's say you have an R chloride. We're gonna need a Lewis acid. For Friedel-Crafts, he always used aluminium trichloride. So you'll end up with the R group there. The chloride is gonna fall off. Okay. So the electrophile here is a carbocation. And all these summary of reactions, you'll see them at the end of the chapter of your book, if you read it, that is. So specifically, instead of using R, let me use like isopropyl. Okay, the 3 carbon represents the R group. So if I have this and I have AlCl3, the electrophile will have to be the carbocation of isopropyl, because I assume the chloride will fall off. Okay, so which means I put the isopropyl on my ring, because that's the electrophile that needs to replace this hydrogen. Alternatively, under alkylation, you use an alkene. You use an alkene. Okay, use an alkene. For example, I'm gonna use this as a basic alkene, the propene, but it has to be in acidic medium. So remember Markovnikov rule? Basically what the alkene will do is gonna pick up the hydrogen by Markovnikov addition. So here you have 1 hydrogen, here you have 2. So this hydrogen in question should end up where there's 2, and then the plus sign will end up on the other side. So again, here my carbocations for this specific example is the same isopropyl. So my product will be the ring with this group attached on it. So this is acid catalyzed alkylation of the benzene aromatic ring using alkenes in presence of the acid, of course. So these 3 and 4 are under alkylation. Okay, this is halogenation. And then there's another one, nitration. So in nitration, you simply react your ring with a combination of nitric acid and sulfuric acid. Okay, so sulfuric acid will be used as a catalyst. So when nitric acid and sulfuric acid combine, they give you this electrophile NO2 plus. That's what's gonna go on your ring. Okay, so NO2 will be there, NO2 plus. I mean, the plus is not there, it's just NO2. Once it attaches, the plus, it's not there. I'm just giving you a summary. Okay, so that's nitration, you're adding NO2. So the last one that we discussed was sulfonation. So you have your benzene ring, and then you are reacting your benzene ring with SO3, but this SO3 must be in sulfuric acid catalyst medium, must be catalyzed by sulfuric acid. So basically, eventually the aromatic hydrogen, this one, is gonna be replaced by SO3H. So your electrophile will be this SO3, or if you want to look at it in a different way, it's gonna be that. Okay, that's what gives you the sulfonic group. So now that we've revised what we discussed, we should move forward. Notice that there's no substituent sitting on the ring. What if you already have a substituent on the ring before you do these reactions? Where will the electrophile end up? So we'll look at directing effects based on the rates of reactions. So the reaction, the electrophilic aromatic substitution, depends on the attack of the electrophile on the benzene ring. This means that the charge density of the ring will be very important. So basically, what I've done in the review is to show you that benzene should be a nucleophile, and nucleophiles must be electron rich. So any group sitting on the ring that's gonna donate electrons will gonna make the benzene ring more reactive. Any group that sucks electron density from the ring, okay, whichever place it's placed, any electron withdrawing group is gonna make the ring electron poor. So when the ring is electron rich, that's reactive. When the ring is electron poor, that ring is deactivated. Okay, and that's what's shown on here. Groups that increase the charge density will speed up the reaction. Those are EDGs, electron donating groups. And those that decrease charge will slow it down. Those are electron withdrawing groups, EWG. So I want you to know that if you have an element directly sitting on the ring, that element having lone pairs will be activating the ring by resonance, because you see, I can push electrons into the ring. So this OH group is an EDG, electron donating group. It's donating by resonance. The alkyl groups, for example, methyl group, will donate through bond. We call it donation by inductive effect. But that's not as effective. That's not as activating as the one that donates by resonance. Any element that has a lone pair on it directly bonded to the ring will activate the ring by resonance. R groups will activate the ring by inductive effect. Always resonance trumps over inductive effect. Hydrogen sitting on the ring and substituted benzene ring is just a reference. Okay. Now, halogens like chlorine are special. We know that halogens are on group 7. They are further to the right of the periodic table. Electronegativity increases across the periodic table, so they're electron withdrawing. So one would expect them to be very deactivating, but they are not very deactivating because they do have 3 lone pairs. So as much as chlorine is sucking electrons out of the ring, it's deactivating it, yes, but that effect is cancelled by the electrons which can be donated into the ring. So that makes halogens weak deactivators, because as much as they're pulling electrons out of the ring, they do have lone pairs that can be donated back into the same ring. So they are weak deactivators. Okay. Nitro, you see in the nitro, the nitrogen has a plus sign on it. That is a very strong electron drawing group. And in fact, you can withdraw by electrons. So here you have withdrawal of electrons by resonance. In fact, it's both resonance and inductive effect. But like I said, always resonance is powerful. It's powerful. Like I said, always resonance will trump inductive effect. So this is a very, very strong electron drawing group. It's a very, very strong deactivator. The nitro group, NO2, kills the ring. OH helps the ring to react. Of course, when you draw resonances, you're going to get this structure. When you draw resonances outside the ring and open up the pi bond towards the oxygen, you're going to get this structure. These ones don't have resonances. Okay, so one would want one that has more electron density. Obviously, if you're looking at benzene, because this is just a hydrogen, and then you're looking at toluene, where the alkyl group can donate through bond. So all these two, these first two, you see that the electrons are right there in the middle of the structure, but here the electrons are outside. You see the electron density is outside the structure. This is the case where you have NO2. So NO2 is deactivating, is pulling electrons outside from the ring. So you have this ring deactivated. You see the blue part is very, very positive. So this ring is deactivated. It has less electrons inside it, so which means it's deactivated. The brown yellow part is the electron density region. This ring is active, can do electrophilic aromatic substitution at a quicker rate. Similarly, here you have electrons, so this one is active. And you have the alkyl group here, in this case is a CH3. You have the R group. R groups are ring activators because they donate by inductive effect. They donate through bond. That's inductive effect, as I explained right here. Because this ring here is basically this cartoon here showing you that you do have electron densities at the ring. So this ring can play the role of a nucleophile. This can easily play the role of a nucleophile. This one would struggle to play the role of a nucleophile because there's less electrons inside it. So there was an experiment that was done to see the effect of these groups sitting on the ring before you do electrophilic aromatic substitution. So first, toluene was taken and was reacted. Toluene. So toluene was taken and reacted with Br2 and FBr. Of course, this is halogenation. And when I started the lecture, I already gave you the reminder and told you that the electrophile here is going to be Br+. This combination simply gives you Br+ that will be used to replace one of the hydrogens in the ring. So when toluene was reacted with it, it was found that the bromine, the electrophile, ended up mostly here and here, like on the second position and the fourth position. I want you to pay attention here. The third position over only gave 3%. This position is called mera. So the mera product was not favored. But the ortho, we said ortho is next door to the reference group. Mera is like after 2 carbons. Para is the substituent sitting on 4th. So in other words, whenever you have an alkyl group, most likely the electrophile will end up on the ortho and the para position than the meta position. So that's called regioselectivity. The electrophile ends up on a certain region, certain area of the ring, preferably than another position. So the R group is an EDG. So this kind of gave a hint that whenever you have electron donating groups, the EDGs, the incoming electrophile will either be on the ortho position or the para position, giving you a mixture of products. Rarely will the electron donating groups presently sitting on the ring give you the meta substituted product. So ortho, para directors are always electron donating groups. Key point: ortho para directors, they direct the electrophile, ortho position and para position. So ortho para directors are always electron donating groups, including the alkyl groups OH, NH2. We'll look at the table shortly. Now, in another case where you have CF3, for example, you're replacing the 3 hydrogens with 3 fluorines. So let me clearly just draw the fluorines so you'll see them. Let me get rid of the 3. So fluorines are the most electron withdrawing elements. So they'll pull electrons out and they're pulling through bond. So the CF3 is an electron withdrawing group, and it has to be strong because it has 3 strongly electron withdrawing elements. So the ring here is deactivated. The ring is deactivated, okay, because you have a group that's withdrawing electrons, electron drawing group. We are doing the same reaction. We still expect that our electrophile will be Br+. So one of the hydrogens on this ring, one of the 5 hydrogens, there are 2 here and there's 1 here, 5 hydrogens. One of those will be preferably taken out. So which one is that? Now, it turns out that whenever you presently have an electron drawing group presently sitting on the ring, the electrophile ends up on meta position, the 3rd carbon from your reference group. Our reference group here is CF3. It's already there before the reaction. So here, this is ortho, assuming we got an ortho, assuming we got a meta, and assuming we got a para. All these are product mixtures. So reflect or focus on the percentage yields. You see the ortho product and the para product are very less, in fact negligible. So in this case, the meta product will be the major product. Why did we get the major product as meta? It's because we have electron drawing group or presently sitting on the ring. So I'm going to write the statement here like I did up there. So meta directors are always electron drawing groups. So I just like using EWG. They are always EWGs. So like the CF3 is an example of a electron drawing group. CH3 is an example of a electron donating group, but those are not the only ones. So in summary, if you have an electron donating group sitting on the ring, the incoming electrophile is gonna substitute the hydrogen on the ortho and the para positions. So that's what we did here. Ortho, hydrogen, this hydrogen could be replaced, or this hydrogen could be replaced to get the para. So for electron drawing groups, the meta hydrogen can be replaced. So you either replace the one to the left or the one to the right. Okay, because the meta can be the 3rd carbon or the 5th carbon. Ortho can be the 2nd carbon or the 6th carbon. So these This Br could as well even be on this other side. It's ortho, it doesn't matter. Okay. So turns out there's a table in your book. This is a very important table. You want to look at it. Okay. So the electron donating groups control the rate of reaction, and not only the rate, they also direct the incoming electrophile at a specific area of the benzene ring, either orthopara or meta. So the reference is the hydrogen atom. So we're comparing relative to hydrogen. So hydrogen will be somewhere here on this line. That's where the benzene ring will be. Okay. But here, probably you have benzene ring with an NH2 on it. You have benzene ring with this group on it, or benzene ring with the OH on it. So these bonds are just cut from the ring, but the ring is there. So assume you presently have these groups on the benzene ring, okay? So how will they direct? Turns out the ones from the amines to the halogens, all these classes of substituents already sitting on the ring will direct ortho para. Okay, so all this area, you expect them to direct ortho para. Okay. Now, where you have electron drawing groups, like here, the carbonyl directly bonded to the ring, you expect electron drawer. Same thing with here, there's electron drawer, electron withdrawal. If you have a ring here, there is electron drawer, and in fact, in this case, it's gonna happen by resonance. So you're withdrawing electrons from the ring. Nitro, the nitrogen has a plus sign. That's even worse. We want lone pairs, we don't want plus charges. So you expect this one also to be drawing electrons to quench the plus sign. So all these guys are strongly deactivating, and they must direct the incoming electrophile meta position. So you have to know this table. You have to know it. You really have to know it. I say one more time, you have to know how to use this table. Notice there's a where you have the strongest electron donating groups, like the activating groups, you'll see that the elements have at least a lone pair that can be taken into the ring by resonance, right? You see that? See that? These are RQ groups. You can't do resonance with them, but they donate through bond, okay? Like we said, the methyl group donates through bond. Let me take you where we did it. See here, the methyl group is donating through bond. It's an orthopara director. Same thing here, it's donating through bond. So methyl group is right there, is an alkyl. So R groups are electron donating groups, they donate through bond. So we'll have to explain again. So there's two effects that we've observed. So either you are donating through bond by inductive effect, that's donation through bond, or you're withdrawing. Okay, so if you're withdrawing, then this becomes an EWG. You're withdrawing electrons through bond. Here you are donating through bond. Here you're withdrawing again through bond. But halogens are special. Even though they're withdrawing, they are taken to be directing orthopara. That's a catch right there. Why? Because they still have lone pairs. They're strongly withdrawing, yes, but the lone pairs cancel the withdrawal effect. So we assume they're electron donating, therefore they will direct the incoming electrophile orthopara. So here you can push electrons by resonance, which makes nitro a very strong electron drawing group. This one, same thing. This one, same thing. You're pulling electrons out of the ring by resonance. So I would expect as a review, I would expect these three guys to direct the incoming electrophile, whichever reaction you're doing. I will expect that the incoming electrophile will be directed meta position on position 3 or 5 of the ring. And like I said, the halogen is special. It's still going to direct orthopara even though it's electron drawing. And then this is electron drawing, so I'd expect it to direct the incoming electrophile meta position 3 and 5. This electron donating, so it should direct the incoming it should direct the incoming electrophile on position 2, 4, or 6. So position 2 and 6, those are orthos. Position 4 is para. Okay, so electron donating groups are ortho para directors, electron drawing are meta directors. So I've talked about the resonance effect. That's what's happening here. So usually withdrawal or donation by resonance will trump donation or withdrawal by inductive effect. Okay, so we've discussed about that. Okay, we discussed about that. So, but now let's see. Why do electron withdrawing group deactivate the ring, and why do they direct the incoming electrophile onto the third carbon, which is meta? So let's look at NO2. So NO2 is a very strong electron withdrawing group. So if you try to understand why, let's say if you had an NO2 and you do halogenation, for example, I think that's an easy example to use. The question is, why will the Br end up on position 3 or position 5? Why? This circle simply means these double bonds go round and round. It's nothing fancy about that. So why is this electrophile put there? Alternatively, I would put it on 5. Why do we put it on meta position, either here or the other side? Now let's look closely. Okay, so if you have NO2, so you're pushing electrons this way, and that opens up, you get a plus sign here, right? Still, I can push this one here and get the plus sign. Let me show you. You get a plus sign down here, and I can push it here to get the next electron drawing, the next resonance structure. Like I said before in earlier lectures, you have to practice drawing resonances. You're gonna need that throughout the class. Okay, I end up with that structure. So what I want you to notice is that if you're pulling electrons from the ring, you'll always end up with a plus sign on position 2, on position 6, or position 4. Now remember, your electrophile, like from this reaction, the electrophile is Br+. So do you think that the Br+ will want to come to position 4, where there's a plus charge, position 2 and 6 where there are plus charges? That's won't happen. Like charges repel. The Br+ won't come where the pluses are in these resonance structures. It's gonna go elsewhere. And now look at the structure. Which position did we not end up with a plus sign? Obviously position 5 and position 3. See, you always see position 5 and 3, no plus sign. Okay, position 5 and 3, no plus sign. Okay, but you've had a plus sign on position 2, 4, and 6. So that's why the electron withdrawing groups direct the Br or the electrophiles on position 3 and 5, because whenever you have electron withdrawing groups, the plus sign will always be on position 2, 4, and 6. the electrophile itself is positively charged. It won't want to go where the plus sign is on the benzene ring. It goes where the plus sign never ended up, which is position 3 and 5. And that's why electron drone groups direct the incoming electrophiles like Br plus on mera position, which is position 3 here. You could as well put it on position 5, is still mera. Okay. Now, for electron donating groups, let's use a lone pair and do resonance. For example, if you have an OR group or OH group. So this could be a carbon containing or hydrogen. So you push here, electrons comes here, you get this structure. Okay. And now again, this can be pushed here, and then you get your next resonance structure, which will be, let me see if I can squeeze it right here. The electrons will be here. This is not disturbed. You made a new pi bond there, and then you have what you got from the first mechanism. And then if you push the lone pair here, okay, if you push this lone pair there, this pi bond opens up, goes to the next carbon. So now in this case, we don't have plus charges like we had here. In this case, we have negative charges. And if your electrophile is positively charged, it's going to be more than happy to attach to where the negative charge is. So now let's look at the ring resonance structures and see where our negative charge is. Okay, so our negative charge is on position, first here it's on position 2, and then it's also on position 4 on this structure, and it's on position 6. Position 2 and 6 is ortho. Position 4 is para position, directly opposite to our reference group. Okay, so that's why the electrophile, whenever you have EDG, the electrophile will end up on position 2, 4, or 6. The two orthos or the para, because that's where you have a negative charge. You know, the electrophile is positively charged. This time the electrophile will be attracted to where the negative charge is. Here the positive charges were there because we were pulling out electrons. Here electrons are there on the ring because we are donating electrons. So here the electrophile will be repelled by the positive charge, so the electrophile goes elsewhere, position 3 and 5 mera. Here we have the negative charge on position 2, 6 and 4. That's where the negative charge is. You expect the electrophile to end up there. Same applies to amines, and same applies to chlorines. Okay. So if you were to draw the resonances and count and see where the charge distribution is, so assume you have an R group, right? And you do nitration. So let's assume you're putting the nitro group on ortho, because we know R groups are electron donating groups, so they should be ortho para directors. So let's attack our nitro, right? Of course, the reagent to make the nitro will be nitric acid and sulfuric acid. That's where I started with the review. So attack the nitro, you get a plus sign on this carbon. The nitro ends up on the ortho position. That's what we have here. And then this first structure can do resonances. You push the arrow there, the carbon behind, it will be one bond less. Okay, so we give it a plus charge, and then you can push another arrow. This carbon behind will be one bond less. It takes the plus charge. Okay, and if you push this back, you end up with this. You push this back, you end up. If you push this back, you end up with that. So those are the three resonance contributing structures whenever you have an alkyl group. Notice that the plus sign is not on the same carbon as NO2. If you were to do the mera, before I talk about the para, I want to talk about the mera. If you are to do the mera substitution, So assume you are attaching NO2 plus. So we are attaching this NO2 on the carbon number 3. Okay. So if you use this pi bond, of course the ring is used as a nucleophile. If you use this pi bond and do the wrong thing and assume mera, we know this electron donating group, it should direct ortho para, not mera. So let's assume you're doing mera. Let's see why that's a problem. Then you're gonna get this NO2 here. The hydrogen is there. There's a hydrogen here. It's just not shown. Okay. And the immediate structure that you're gonna get from here is gonna be this structure here. And if you push this bond here, okay, you end up with this resonance structure with a plus sign where the bond left, because it's one bond less. That carbon is one bond less. And then push this double bond here. The carbon behind here will have a plus sign because it's gonna be one bond less, which is this. Okay. But if you want to get this structure, you can push this bond here. Assume this was not shown. You can push this one here. Then this hydrogen will get a plus sign, which is this structure. What I want to show you is that here, you'll never get the plus sign sitting on the carbon where the electron donating group is. You see how this plus sign is next to the electron donating group? That's good. You want that. Same here. You see the plus sign. If you're assuming para substitution, one of the resonance structures will have the plus sign sharing the carbon, the electron donating group. That's good. What does electron donating group do? It neutralizes the charge. If it's donating electrons, the plus charge is neutralized. So you want that. Do you see any of that type of structure here? Nope. None of these plus signs is sharing a carbon with the electron donating group. And that's why the ortho para products will be the major. So whenever you react toluene with nitro group from nitration, then you'll expect either the ortho product or the para product to be the major. Very little of the mera product will be observed. The nitro sitting on the third carbon will be very rarely formed. So that justifies, again, I repeat, this slide is just explaining how ortho para directors are preferred over the mera whenever you have an electron donating group like a methyl group. You will see that in our resonances, the plus sign is sharing a carbon with the electron donating group. You want that because those electrons that are donated on that carbon will quench the plus character, reducing the activation energy and making the reaction go faster. Here, the plus signs are they can never be on the same carbon as the electron donating group, which in this case happens to be the methyl group. So the plus sign is not stabilized. Therefore, the mera product will not be preferred whenever you have electron donating groups like alkyl groups, OH, OR groups, and amines. Okay. So like I said, once you do your reaction, so for example here, if you do bromination and assume orthobromination, so let's say we're attacking this, there's a hydrogen here. So let's say you're attacking the Br plus, maybe the reagent was Br2, Fe, Br3, that's what gives you Br plus. So if you do orthobromination, the bromine ends up on second carbon, the plus sign ends up where the electron donating group is. I told you OH is a strong electron donating group because the element oxygen has a lone pair that can be donated by resonance, right? So here at least you see a plus sign on a carbon attached to the same carbon as the electron donating group. You see a plus sign sharing a carbon with the electron donating group. You want that. You want that. That's good because now the electrons can quench the plus character. If you decide to do what's called para bromination with the same phenyl ring, Okay, so let's say we have this ring and we want to do bromination. So the ring will use the pi to attack a Br plus. Probably you're gonna get this as a first resonance structure, and then you can push the electrons around. When you're done pushing, you'll see that again the plus sign in one of the resonance structures is sharing this a carbon with the electron donating group. You want that. Okay, here even it's better because the plus sign is put outside the ring. So if you decide to do meta substitution, so let's say you want to put the bromine here, which is wrong whenever you have electron donating groups. If you do meta substitution, you put the bromine here, you'll never see the plus sign on these resonance contributing structures on the same carbon as the electron donating group. The plus sign is not on the same carbon as the electron donating group like we saw here. The plus sign is, you see the plus sign here, it's next to electron donating group. You don't see that situation here. So again, it's emphasizing that whenever you have electron donating groups, you expect ortho-para products. So in this case, I would expect from the reaction, if I'm doing the bromination with the electron donating group like OH because of presence of lone pairs, I would expect to see the ortho, ortho, where the bromine is next door, and the para where the bromine is on the fourth carbon, because at least the resonance intermediates have the plus sign on a carbon as the electron donating group. Okay, so I hope I've convinced you why the electrophiles end up ortho or para. Now let's take the case of electron withdrawing group already sitting on the ring. If you have an electron withdrawing group already sitting on the ring, then I would not expect ortho-para products. That's what we said, right? Let me show you. Where did we look at it? That's what we said right here. That's what we said right here, because CF3 was an electron withdrawing group. You don't see much of the ortho and para. You see much of the meta product. Okay, so NO2 is one of the very strong electron withdrawing group. So I would expect NO2 to do meta. Now let me start by explaining why meta is good. So this is an electron withdrawing group. Okay, looking at our table, NO2 is right here. So assume you have the ring. Presently, if you do a reaction, you expect the electrophile coming from the reaction to go on the meta position, to attach on the third or fifth carbon. The reason being, whenever you do your meta substitution, let's say you have NO2 plus here, you know how NO2 is made. The combination to make NO2 plus electrophile is nitric acid and sulfuric acid. Again, that's why I did the review before the first few minutes of this lecture. So if you do meta substitution, meaning we are putting the NO2 right here, so the plus sign will be, this is gonna be your first resonance. The way I've pushed my arrow, you'll first form this. The plus sign will go here, because the NO2 is going on the other sp2 carbon. And then you can do resonance. This comes here, you get this structure, and then this can come here to get this structure where this carbon will be now one bond less, then you get a plus sign. So this arrow, if you push this one here, you're gonna get this structure, and it's gonna be repeating itself. So notice that the plus sign is never on the same carbon as the electron withdrawing group. You don't want that. You see, in this case, if you do ortho, let's do auto substitution. If you do auto substitution here, the nitro will end up here as this hydrogen, the plus sign will be here. So you end up with this structure. See how the nitrogen has a plus sign, and now you've put a plus sign there. Do you want two equal charges close by? No, that does not happen, should not happen, because the equal signs will repel. Now, same thing, if you do auto substitution, one of the resonance contributing structures will be very close to an electron withdrawing group. So let's say you have NO2 to react with this ring, and this time we are doing para substitution. So we use this pi bond to attack the nitro. The immediate product that you'll see is gonna be this molecule. And then you can draw resonances. Push this one here, you get this one. If you push this bond here and keep this double bond, you're gonna get this. You see, again, there's a problem here. Okay, there's a problem there because one of these resonances is putting a plus sign next to the next to the N plus. So again, this is positively charged, this is positively charged, like charges repel, this structure is invalid. So you're only left with two valid structures, but with meta substitution, all the three are valid. So that's why whenever you have electron drawing groups, the electrophile will want to go meta. So in this case, the product would have been, of course, your NO2, your original NO2 will be there, and then the one that was added after the reaction will be on the meta position. Because all we need to do to finish up the reaction is to put a base that will take out this hydrogen and make a double bond. Then you get your final product. So that's sitting on meta. You are not going to see NO2 put, it's rare to see the NO2 put on the auto position, unlikely, or putting the NO2, or in this case I'm saying putting the electrophile on the para position. So the bottom line is, whenever you have electron drawing groups, generally the incoming electrophile, e.g. NO2 plus, Br plus, Cl plus, and carbocation, those ones will be directed meta, not auto-para. Okay, so electron withdrawing groups will direct electrophiles on meta position. So they are meta directors. So, and remember, the meta position of the benzene ring is position 3 and 5. Okay, so a good example is shown here. So let's say that these are your R groups. Okay, if they are R groups, then I expect they are auto-para directors because there's donation. So I would expect to see much of the ortho and the para and less of the meta. You see how the percentage of meta positions are less? So assume that the R group is CH3. Assume that this guy is CH3. CH3 is small, so you'll see much of the ortho than the para. Remember, I'm disregarding the meta because R groups are auto-para directors. I don't expect meta. Now, if you increase the size of the R group from the methyl to ethyl, this number decreases. The auto position now becomes less. In fact, it's almost 1-to-1 comparing putting the nitro group. Remember, the electrophile is here is NO2 plus. So if you put the NO2 next door and put it on the fourth position, whenever you have an ethyl, you get 50-50% equal mixture. But if it's a methyl, then there's less crowding, then much of the NO2 will be on auto rather than on para. If you continue increasing the size, so let's talk about the last R group. If this is your R group, okay, now that becomes too big, so you'll have these alkyl groups here. It becomes too big. That means if you put the nitro group on auto position, that NO2 is going to be crowded, and that means that the auto position will not be favored. Much of the product would be para because now the NO2 is further away from the bulky group. So as much as we are looking at directing effects, one wants to look at crowding or rather steric effects. Okay, crowding. So if the group is big and you are expecting orthopara, the para will win. If the group is small and you're expecting orthopara, the ortho will win. Okay. So benzene is not the only aromatic compound. You have naphthalene, you have anthracene, and these are usually used to make mothballs. You have pyrene. The problem is that much of these structures that have fused benzene rings are carcinogenic. If you breathe them, you eat them, you get cancer. And they are applied widely. They're applied widely. For example, these combined aromatic structures, this one looks like a tube. They are very, very, very important as what we call electrical wires. They are used as wires, okay? Electrical molecules. They're molecules, but they're used as wires. So we use these in nanochemistry as superconductors. They're used in supercomputers. They're used to make bombs and all that. These compounds have interesting properties in electrical conductance, and they are very high strength and highly durable. So I'm just highlighting some uses of some of the polyarenes or polycyclic aromatic compounds, PAHs. So as much as some of them are carcinogenic, like they can cause cancer, some have found a lot of use in electrical uses of making material in material science. That ends our chapter 4.